Hello and good day everyone. So our topic for this video will be about wind loads on structures according to NSCP 2015 provisions, directional procedure. Okay, so in this video, we will begin with an introduction to structural wind load assessment. Then next, we will be discussing about the procedures that we could use if we are to comply with NSCP 2015 provisions. Then we will be proceeding with the computations using directional procedure. Okay, so first things first, what is wind? So basically when we say wind, it is moving air. Okay, so as we know that air is that something that is very light, and that is something that we could not see, but of course we could feel it. But why would we incorporate wind loads in our designs? Considering that air is nearly weightless, so napakagaan po. So the reason why we would be incorporating wind into our structure is that because if wind hits a building, so pag nabangga po niyo yung building, it has a tendency to push the structure towards the direction of the wind. So for example, that this here is your structure, and if wind travels from this direction or from this point to this point, it has a tendency to push the structure towards this direction. And on the other side of the wall, it also has a tendency to pull it. So later on that. So from it, guys, we could also say that even though that wind is rather very light, the greater the surface area that a wind would hit, so the greater the surface area, the greater the resultant of the load. So yun na po yun. Basta yun na yun. So why would we consider wind loads? Para na din may ma-upload akong video. Okay, so anyway, before we could proceed to the code provisions, we must be familiar with these technical terms first. So first one here, we have here the MWFRS, or the Main Wind Force Resisting System. So when I was still in college, I actually called this as Monday, Wednesday, Friday, rest day, and Saturday in order for me just to memorize it. However, if you would be asking me, I would rather tell you that instead of you thinking of it that way, just read this, no? Ito na lang po yung intindihin nyo. Itong concept po na to. Okay, so we have two technical terms here which we call MWFRS. And as for the other, we have here the components and claddings, or CNC. Okay, so what are their differences? So when you say main wind force resisting system, so as per sbcmag.info, this applies as the assembly. Okay, so we have here a root word, assembly, of multiple parts. Okay, so it also provides support and stability for the overall structure. So in contrary, for components and cladding, CNC, these are the elements of the buildings that do not qualify as MWFRS, and in other words, this covers an individual part. So if you would just be reading those statements, we could now say that for components and claddings, individual, and for MWFRS, assembly or system. So parang by group siya. So maybe if we would be comparing it with other terms, parang yun dun sa components and claddings, let's say individual member lang siya, or let's say a beam, just a beam. And as for MWFRS, that is the whole structure, and it for example, a frame consists of multiple structural elements such as beams, columns, shear walls, and etc. Okay, so if you want to know the effects of a wind to the overall structure, you would now be making use of main wind force resisting system. But if you want to know the effects of wind towards an individual component, then use CNC, or components and claddings. Okay, so for claddings, guys, cladding is basically paano ba explain? Google yun na lang. So for claddings, if you would be going to let's say structures, meron yung mga ibang mga structure na yung wall nila dun sa labas, they have a plastic material. Those are what you would be calling claddings. Okay? So again, Google nyo na lang po. Nakalimutan kong i-Google. Okay, anyway. So, as per NSCP 2015, these are the permitted procedures that we can use in our design for wind loads. Okay, so for MWFRS, we have four permitted procedures. So we have one, two, three, and four. So for the first one, this is what we would be calling directional procedure for all heights. For number two, we have here the envelope procedure for low-rise buildings. Then number three, directional procedure for building appurtenances and other structures. Then fourth, we have here the wind tunnel procedure for all buildings and other structures. Okay. As for CNC, we have here the analytical procedure and the wind tunnel. So as you can see here, for with the wind tunnel procedure, we could use it for both MWFRS and CNC. But then again, if you would be looking at the title of the video, we are to focus here on the directional procedure. Okay, so if you would be comparing directional procedure to that of the other procedure, which we call envelope procedure, though envelope procedure is the much easier methodology in you solving for wind loads, I should say. For the directional procedure, this is a lot more versatile because you could actually use this procedure for all structural heights. Whilst that of envelope procedure, you could only make use of it if you are to consider just low-rise buildings. So for directional procedure, you could use it for low-rise buildings, mid-rise buildings, and high-rise buildings. Okay, so let us now proceed to the wind load applications using directional procedure. Okay, so suppose that we have a building here, and let's say that wind will now be traveling from this point towards this point. So I'm not sure if you will be able to see an arrow here. So hoping that you did. I actually draw a red arrow in this direction. Okay, so if wind travels from that direction, of course it would be hitting a wall. And the first wall that it will be hitting, which is this particular wall here, that is what we would be calling the windward wall. Okay, so the windward wall is that wall that is subject to direct pressure. So direct contact po sila ng hangin, and the tendency of wind towards the windward direction, the windward wall, is that it is actually pushing the windward wall. Okay, but then again, if wind travels towards this direction, so aside from it pushing the windward wall, we also have this term which we call leeward wall, which is opposite the windward wall. So the leeward wall is actually located here at the opposite side. And even though that the wind is not directly hitting the leeward wall, the tendency of wind is that it is producing a suction pressure towards the leeward wall, I should say. In Tagalog, parang hinihigop po niya. So, suction. So, suppose, guys, that we have another structure here. If wind travels towards this direction, and let's say that this is the windward wall, the opposite side of it would be called as a leeward wall. And the tendency of wind is that it would now suck the building towards this direction. Suction nga po kasi. So, parang higupin po niya papunta sa direction na yon. Okay? So, again, we call that as leeward wall. And as for this side, so, I hope that you could also see this yellow area that I am shading right now. So, brace yourselves for the term. Medyo mahirap po itong ma-memorize. So, the term for this wall here at the side is very hard to memorize, and it actually causes depression. Joke lang, no? Anyway, so we call that side wall. Okay? So, very hard to memorize. That is the wall at the sides. Okay? So, take note of those wall surfaces which we will be using in our computations later on. Okay, so proceeding to our building here once again, and in our building here, suppose that this is the front view. And again, let us assume that for this particular building, suppose that wind now travels towards this direction. If wind travels towards this direction, again, we call the surface on the left as windward wall, WW. And for the other side, we call this as the leeward wall. And this surface in front of us, we call this as the sidewall, even though that it is located at the front, not the side. But in terms of the wind here, that is this surface here is actually the side. As well as for the other side, yung back side po. In this case, since wind travels towards this direction, the other side would now be called as, also called as the sidewall. Okay, so what would be the, what you call this, what would be the appearance of the pressure if ever that we would be seeing it? So as per NSCP provision for directional procedure, it is said there actually that for the first few meters of the building, so suppose that this is that few first meters, which is 4.5 meters. And if you would be opening the NSCP or the code to the other pages, in some pages, they say that that should be 4.57 meters. So, depending on your reference on NSCP. So, sa ibang page kasi 4.5 sabi. Sa ibang page, 4.57 yung sinasabi. However, guys, ulitin ko lang, for this height, it was indicated there that the building is actually experiencing a constant amount of pressure. Though my drawing is not really perfect, let us assume that this is perfectly vertical. So again, that is constant. Then um, as we analyze the remaining height of the building, the tendency of air is that it would now increase its pressure as we go up in height. Okay? So from that, guys, it would now look like this. So the higher the height of the building, the greater the pressure that it would carry in terms of windward. Okay? But as for leeward, it is also indicated in the code that for leeward pressures, regardless of height, it would now carry a constant pressure. So same lang po sila. Okay? Unlike for the windward, whereas the constant pressure would just be for a few meters, 4.5 or 4.57 meters, once again depending on your reference. So again, if I mean the higher the building, the greater its pressure. But for leeward, it would just be a constant pressure throughout. Okay? So for the fundamental formula for the directional procedure, it would now look like this. So itong dalawang ito po, yung main fundamental formula po natin for wind load pressure. Okay, so the wind load analysis formula using directional procedure is rather straightforward. So just memorize this formulas, or formula I should say, substitute all the values that you know, then that's it. You have actually solved for the pressure. So in this case here, in our slide a while ago, this is what we would be solving. Whatever, or what is the pressure at this point, pressure at this point, pressure at this point. So basically, we are solving for the pressure P. Okay? So the pressure P is given by the equation Q sub Z times G times Cp plus minus Qi times G times Cpi. And from that, guys, we could solve for the value for Qz using this equation. Okay, so let us focus our, or let us put our attention to this formula first at the top. So P is the wind load pressure, and the value that you will be solving here is in terms of Pascal only, okay? Not kilopascal, just Pascal. Then as for QZ, so QZ is the velocity pressure evaluated at height Z, okay? So in our case earlier, so if you would be analyzing this part here, and you would be comparing it with this part here, as you can see, guys, this part would have a higher height. So this part here would have a higher height. And thus, this is what you would be calling, this height here is what we would be calling Z. Okay? So again, going back here, So that is the a pressure evaluated at height z. Then next up, we have here the gust factor. Then Cp, we have here the external pressure coefficient. Qi, internal velocity pressure. Cpi is the internal pressure coefficient. Okay, so we would be, I would be explaining this to you as we go through the video and as we go through the lecture. Okay, so again, we would be needing this equation here in order for us to solve for this equation, because as you can see, Qz is to be used in this equation. Okay, so in this equation for QZ is equal to 0.613 times KZ times KZT times KD times V squared. So take note that this equation can only be used using SI units or metric units. So if you would be using English units, this value here would now be different. So if I'm not mistaken, that is 0.002 something. Okay, but then again, as per NSCP provisions, 0.613. Okay. Okay, so what is 0.613 in the first place? So for 0.613, this takes into account the mass density of air for standard atmosphere, and in some cases, they call this as the mass density coefficient. Okay, but take note that this is only used, or this 0.613 here is used for metric units only, and if you would be making use of English units, you would be using the value 0.00256, I think. So let us check that later on. And next, after 0.613, we have here the value for KZ. We call that as the velocity pressure coefficient. For KZT, that is the topographic factor. For KD, that is the wind directionality factor. And for V, that is now the basic wind speed. Okay, so let us first consider this equation here for QZ, and let us discuss all of the variables from right to left. Okay, why right to left? Wala lang, trip ko lang. So I think all of us would agree that the faster the speed of the wind, so I think that is kind of redundant. So the faster the wind, the greater will be its impact to a structure. So in Tagalog or in Filipino, pag mas mabilis po yung hangin, mas malakas po yung impact niya doon sa structure na kino-consider nyo. Okay, so thus it would now result to a higher wind load or a higher pressure. Okay, so from that, guys, this V here stands for, again, basic wind speed, and it is taken into consideration the speed, kung gaano po kabilis yung hangin. So take note that if you will be making use of this formula here, the value for V must be in terms of meters per second. Okay? So again, meters per second. And the next question is, how would we now check for the basic wind speed of, let's say, wind on your project, whichever it is in the Philippines? So you have plenty of ways. The first way is for you to ask the agency that is measuring wind speeds. The second method is by looking at the NSCP itself and search for the wind hazard maps. And the third is by making use of apps and softwares in order for you to plot the basic wind speeds. So if you would be making use of the NSCP provisions or NSCP NSCP code, we have this map here. And in this map, we could actually extract the basic wind speed depending upon the location of your project. So suppose that your project is located somewhere here. So if you would be zooming in there, so this is now what it would look like. If you are to look closely in your NSCP, we actually have here numbers. So I think this is 270, this is 260, 280, and etc. So for example, that your structure is located here, and if it is located along this line here, which says 280, this 280 here stands for 280 kilometers per hour. Okay, so suppose that the structure is located somewhere here. Okay, So if it is located somewhere here, whereas it is located in between these two lines, so this line on the left is for 250 kilometers per hour, and this line on the right is for 260 kilometers per hour. If you want to have an accurate result, you would now be interpolating between 250 and 260. Okay, so once again, if you want a rather accurate result, you would be interpolating between 250 and 260. So meaning that if, let's say, your project is located exactly at the middle of this line by 250 and 260, meaning that the basic wind speed that you will be using is 255 kilometers per hour. Or if you want to have, let's say, a rather conservative approach, what you would be doing is for you to um, choose the larger value between the two lines. So if this here is 250 and this here is 260, you would rather choose the 260 instead of you interpolating if you want to have a rather conservative design. Okay, but take note once again that the values here are in terms of kilometers per hour, and once again, if you would be making use of this equation here, the velocity, I should say, must be in terms of meters per second. So if we would be converting from kilometers per hour to meters per second, so let us convert hour into seconds first. So I would be multiplying this by a conversion factor, whereas hours would be at the top in order for this to cancel out. And I would put seconds at the bottom part. Or if you do not know how many seconds there is for 1 hour, then maybe just convert it into minutes first, then convert it into seconds. So I'm actually pretty sure that for every 1 hour, it consists of 3,600 seconds. So again, for every 1 hour, 3,600 seconds. So from that, guys, our unit is now kilometers per second. So kilometers per second. But then again, I want meters per second as my unit. So I would be multiplying another conversion factor. And I know that for every 1 kilometer, there is 1,000 meters. So from that, kilometers would cancel out, thus leaving me an answer in terms of meters per second. Okay? So from that, for every 1 kilometer per hour, we have here 1 over 3,000, 1 over 3.6. So 1,000 divided by 3,600. So looking at the calculator, 1,000 over 3,600. We have here 5 over 18 or 0.2778, or rather, we have here 1 over 3.6 kilometers. Meters per second, I should say. So this is now our conversion factor, 1 over 3.6. So you could actually do it this way, or whatever you will be solving for here, just divide it by 3.6. So in that case, for example, 280 kph, just divide this by 3.6. So the answer here is, so again, 280 divided by 3.6. So the answer here is 77.78 meters per second. Okay. So once again, that is for the value for V. So for the value of KD, which is the next one here, KD stands for the wind directionality factor. And this is actually dependent upon what kind of structure you are analyzing. So if you are solving for the main wind force resisting system, or MWFRS, or other components and claddings, you would be making use of 0.85. However, if let's say that you are to design chimneys, tanks, or similar structure, and let's say that it is round, you would be making use of 0.95, and of course, etc. Okay, so that is for the wind directionality factor. Okay, so next up, KZT. So when we say KZT, that stands for the topographic factor. Pero ba't ganun yung H doon, tagilid? Anyway, so di ko alam kung nangyari dyan. Anyway, so again, KZT, that stands for topographic factor. And in some cases, they actually call this as the speed up factor or coefficient in some cases. Okay, so this is given by this equation. Kzt is equal to 1 plus k1 plus k2 plus k3 for structures that is located on hills and escarpments. And if it is not located in those areas, kzt is equal to 1. Okay, so what is the importance of this factor? So suppose that you have here, let's say let me just erase this first, your structure on top of a hill. And let's say that wind travels from this point towards this direction. Okay, so of course, wind will also travel at this location, but then again, this is a hill going up. And from that, guys, the tendency of this wind here is that, of course, it would go up here, and this would also go up here, this would also go up, this would also go up, and this would go to its original position, or original direction, I should say. And as you can see at this very location, the wind is very dense. And from that, with wind speed up happens. So mas bumibilis po siya because of the density of air here. Mas compacted po sila. Okay? So again, we call that as wind speed up. So from that, guys, if that is the case, this kzt, or the value for kzt here, takes into account this wind speed up. Okay, so this is rather an amplifier for the value for qz. So again, guys, this is the formula for kzt, that is equal to 1 plus k1 times k2 times k3 quantity squared. So if this is the hill, let's say that this is the hill, and let's say that your building is located here, then from that, guys, you would be making use of this figure. And let's say that your building is located on an escarpment, whereas we have here a plain area, then it would go up. Then this is also a plain area. Then from that, guys, if this is your building, this is now the figure that you will be using. Then for the value for K1, use this table. For the value for K2, use this table. And for the value for K3, use this table. Okay? So, if ever that your building is located on just a plane, so nasa patag siya, then once again, meaning that you could actually make use of kzt equal to 1.0. Okay? So, proceeding first, since this is just the introduction, proceeding, so after kzt, we now hear the value for kz. So when we say kz, that stands for the velocity pressure coefficient, and it is now given by this equation, whereas kz is equal to 2.01 times the quantity of z, or the height where you are analyzing, divided by the value of zg, which could be seen in this table here, table 207 a.9-1, raised to 2 over alpha, which could also be seen here. Okay, so again, for z, that is the height where you are analyzing. So for example, that in our figure a while ago, let's say that you are analyzing at this very location. Suppose that you want to solve for this pressure, meaning that this is the z that you will be using. Okay, if you are analyzing this surface here, this is the z that you would be analyzing, and so on and so forth. So once again, going back here, that is for the value for z. And take note, guys, that for the values for alpha and z sub g, it is dependent upon the exposure. Okay, so when you say exposure, guys, it is actually given by this code provision, 207A.7.3. So we have here exposure B. So these are for buildings with their mean roof height less than or equal to 9 meters. So this does not indicate that this is your building per se. So anyway, so exposure B shall apply where the ground surface roughness, as defined by surface roughness B, prevails in the upwind direction for a distance greater than 450 mm. So when we say surface roughness B, ito po siya. And as per surface roughness B, it is indicated here that these are for urban and suburban areas wooden areas, or other terrain with numerously closely spaced obstruction. So yan po yung madaming bahay, siguro mapuno masyado. And from that, guys, let's say the population there is dense. From that, we could conclude that it might be surface roughness B. Okay? And for surface roughness C, open terrain with scattered obstruction. So there is still obstruction, but it is of course scattered. Then for surface roughness D, these are flat and unobstructed areas. Okay, so how would surface roughness affect the wind or the wind load that will be applied to your structure? So for surface roughness B, so imagine that you have, let's say that this is the plane where your building is located. So let's say that this is your building, but in that building we have, let's say, a tree here, let's say another building here, another building here, let's say another building here, and etc. So suppose that this is once again, let's say your neighborhood, and if let's say that wind will be traveling from this direction towards this direction, plenty of structures will be obstructing the wind. So basically, um, if you would now be imagining it, the wind, if it would now reach your structure, it might have been reduced already because the surface is very rough. So for surface roughness B, I should say, for surface roughness C, suppose that this is your structure and we only have a few obstructions. So let's say that we have a small plant here, let's say a tree here, and let's say that we have a building at the far side, whereas those obstructions are very scattered, and let's say that wind will be traveling towards this direction. It might have underwent some obstructions, but only a few, and it is scattered. So from that, guys, this is now C. Surface roughness C. This is surface roughness B. And for surface roughness D, unobstructed. For example, bumili ka ng isla mo, sa'yo lang yun. Bumili ka ng desert, sa'yo din lang yun. From that, surface roughness D. Okay? So, again, those are now the variables that we would now be making use, or that we would be investigating in order for us to solve for the value for QZ. So KZ would be unitless, KZT unitless, KD unitless, and for V squared, or sorry, for V, that is now meters per second, so you would be squaring it. Okay, so if you would now be solving for the value for QZ, this is also in terms of Pascal. This is not yet the pressure that will be applied to this structure. Kung ano po yung QZ, hindi pa po yun itong pressure na to. Hindi pa po. Because there are still some other factors that could affect the pressure that is affecting the structure itself. Okay? So that is why for the applied pressure P, you would still be multiplying a couple of factors to the value for QZ in order for you to know the effective, let's say, pressure that will be applied onto the structure.